AP Chemsters, this is Mrs. Vanderlei bringing you the next edition, or hopefully the last edition, of section 16.7 through 16.9. We left off on the last video talking about delta G and what it means as far as being negative, zero, and positive. So I thought it'd be kind of fun to bring that analogy to the roller coasters. So here we go. Here we have the cart is going up the hill. It is not spontaneous. The cart does not go up the hill by itself. It requires work to put this cart up the hill. So delta G is positive here. So we're almost reaching to the top of the hill, and we're going on a curve. Hang on, we're going to go down the hill very shortly. So enjoy the ride. Okay, we're going down the hill. This is very spontaneous. This is where delta G is negative. At the bottom of the hill, delta G is zero. We're at equilibrium. At the top of the hill, now it's spontaneous. Delta G is negative. Bottom is zero. Up the hill is positive. And so it continues. So think of this. Okay, so we're back in our notes right here, and I just wanted to kind of go back and look at the ramifications of what this right here is telling us. Okay, so let's kind of think about this. Let's kind of put another equation up here. So if we have delta G naught is equal to the sum of the delta G products minus the delta the G reactants. If we're at equilibrium, so if we're looking at this first one right here, what does that mean? That if this is equal to zero, then delta G of the products is actually equal to delta G of the reactants. And so that's why there is no shift, that no position is higher or lower than the other. Remember that we're looking to have the most negative overall, and that's what's going to drive this. And so if you have that the Gibbs free energy of the products are equal to Gibbs free energy of the reactants, there is no drive, there is no shifting occurring because they're already equal. But let's look at the next one, where delta G, if it's less than zero, what does that really mean? Well, in that case, if I go back and look at this equation again, if my total values are negative, what exactly does that mean? Well, it tells you that you are having the standard states, the products are actually going to be lower than that of the reactants. So here we're going to have the products are going to be lower than the delta G of the reactants. And what does that really mean? I need to scroll this down to kind of put a picture to this, okay? So if I am looking at a G value here and you know, the amount or something on this side, again, think of that roller coaster idea. And so if I have my delta G products down here and my G of my reactants up here, can't you see that that's where your delta G is negative, where your products, that's a G there, is actually lowered than your reactants. So you have a net products minus reactants, we have a delta G is negative in that particular case. Now, how will that drive the system? What does that really mean? If you have your products lower than your reactants, you are going to favor making those products. And if you recall back when we talked about what the meaning of K is, if you are favoring the products, because that's the goal here, you want that negative delta G, that you are going to drive it towards the products, and so you're going to shift it to the right. You're going to favor those products. Now, the opposite is true if delta G is a positive number. And so the G products is not going to be less than that. They're actually going to be greater than the G of the reactants. And what will that look like on this chart here? So let me draw another graph here. And so it'll look like this. So here is where your Gibbs free energy of the products is at, oops, that's a P by the way, the products is greater than the G of the reactants. And if you look at this difference, when you subtract products minus reactants, you still get a positive number here. And what does that mean? It's going to drive towards the lowest point, isn't it? And your lowest point on this graph, the second graph, is your reactants. Your reactants are lower than your products. So your system is going to go towards the reactants. Your goal is to get to the bottom, really. So if you are going to drive it to the bottom, you're going to drive it to the reactants. So here you have K is less than 1, and the reactants are favored, just like what we had said earlier. So when you're thinking about this, how can you get to that lowest point? All right, well, let's go on. And let's see how this works as far as a problem goes. So we're going to consider the ammonia synthesis, and you can read that. You are given the delta G naught. You don't have to calculate it. And we have a temperature there. And it says, all right, how will the direction of the system shift given this information? So what is it that we really need to solve for? Well, we need to solve for delta G. See if delta G is a positive number or a negative number or equal to 0 will tell us how that shifts. So I'm given pressure, and we learned an equation on the prior page that will help us deal with pressure. And it is right, well, I think it's 2 prior pages now. It's where you have the ln of P as the equation here. Here it is. So this equation right here is dealing with the pressures. And again, you set up these pressure values like you would with any law of mass action and set it up that way. So our first thing to do is solve for that P, or in other sense, solve for the Q, the same thing again. So let's check this out. If I'm doing this problem here, and let's see here, we need to solve for Q using the pressures. And looking at this equation here, it's always products over reactants. And look at my product. It is ammonia gas. So I'm going to put that with 1 atmosphere. And like any law of mass action, I have to look at your coefficient and say, oh, I got to square that. My reactants, I'm looking at nitrogen right there. And my pressure of my nitrogen is 1.47 atmosphere. And my pressure of my hydrogen is 1 times 10 to the negative 2 atmospheres. But what do I have to do with that number? I have to, where is it? There it is. I have to cube it. And when I do all that work, you get 6.8 times 10 to the negative 5th. So now we need to plug that into our equation where delta G is equal to delta G naught plus RT ln of Q. Well, we just solved for Q, didn't we? So we can take this number and plug it in there. What else do I know? I have delta G naught that gave us that number. So it's negative 33.3 kilojoules. But remember what we said, because R right here is measured in joules, we need to convert everything into joules. So it's actually 33,300 joules plus 8.3145 joules per mole K. Looks, that sounds like molk, doesn't it? Times 298 Kelvin times natural log of 6.8 times 10 to the negative 5th. And when you put all this together, go ahead, try this. Plug it in your calculator right now. I'll come back and let's see what we both get. All right, hopefully you paused it and figured out what you get. You get 0. So if your delta G is 0, what does that mean? We are in equilibrium. And if we're in equilibrium, guess what? There's no shift. That's an I there. No shift. So it's not going to favor the products. You're already at equilibrium. You're already there. So let's go ahead and let's do the next one. If you'd like, you could go back and look at that equation again. Delta G is equal to G naught plus RT ln of Q. Now this is a very interesting one. Look at Q. Look at all these numbers. They're ones. So it's equal to 1 atmosphere squared over 1 atmosphere times 1 atmosphere to the third. And what does that all equal? It equals 1. Well, if you plug in 1 here, if you are a math-savvy person, what will you recognize as the natural log of 1? Hey, that equals 0. So what's R times T times 0? 0. So now what? What am I equal to? So delta G is equal to delta G naught. It's not at equilibrium. It's not equal to 0. It's equal to delta G naught. And that works out pretty nice because that's equal to negative 33.3 kilojoules. And you don't need to convert that to joules because your R has been wiped out. And so what does that mean? Delta G is negative. It's less than 0. And if you go back to that prior page, what does that mean? That, excuse me, means that your products are lower on the roller coaster than your reactants. Oops, that's a P though. I did that twice now, haven't I? So that's a P, and that's your reactant. So you're already at your lowest end. It's the products are lower than your reactants. And folks, that's what's going to drive the system. K is going to be greater than 1. And so you're going to favor your products. You're going to shift to your products. You're going to shift to the right. That's what that means. So let's go ahead and work out this next one. And to tell you the truth, this kind of a problem is going to be very, very similar to what you might see on the AP. It's going to be some work here where you have to find your delta H total, your delta S, plug it into solve for delta G, and then compare it to, oh, so that'll be your G naught, and then compare it to your G. So go ahead and solve for delta H, solve for delta S, and then solve for delta G, and see what you can do with this problem. So pause this for actually quite a while and see how you do compared to what I do. Okay, so here we go. I found delta H from products minus reactants. I found delta S to be this, from products minus reactants. Notice a couple things. It's exothermic. Delta H is negative. Notice something else. Entropy went down. And what does that mean? It became less, because negative means less disorderly. Does that make sense? Solid gas to a total solid. So yeah, it is negative because my gas molecules became, in a sense, the solid form. So it went from disorder to order. It makes sense as a negative number. So then I just plugged in these numbers and I got delta G naught at standard state to equal negative 1.49 times 10 to the 6 joules. All right, so then I plugged in those values, but what do you notice? If we're at equilibrium, delta G is 0. And therefore, we are solving for K, not for Q, because at equilibrium, that Q equals K. And now it's just a matter of plug and chug. So I subtracted 8.3145 from both sides. So then I got negative is equal to a negative 1.49 times 10 to the 6 joules. I did all the math, and I got natural log of K equals 601. Hopefully you got the same numbers, because the math isn't that hard at this point. But what is interesting, if you haven't gotten this far, I think it's really cool what happens next. Go ahead, e to the 601. Try it on your calculator. What do you get? You get an error. I got an error. It is too big to calculate. K is huge. It favors your products. What this is really saying, it's going to go to completion. Let's go to the next problem. All right, so what I'm going to do here, I want to solve for K. I want to see how K and T are related. So I'm going to go ahead and divide both sides by negative RT. So natural log of K is H naught divided by negative RT minus T delta S over negative RT. You probably noticed something. T's cancel out. These become positive. And I just want to rewrite this again. So it's delta H over R times 1 over T plus delta S over R. Folks, I'm feeling a graph coming on. Here is your Y, M, X plus B. So if I were to graph this, here is your natural log. Here is your X. It's a negative slope. So your slope is equal to negative delta H over R, and your y-intercept is where delta S over R is. So it's just another way to see how these are related. Now let's go on quickly. I only have about a half a minute to talk about the free energy and work. So what this is, the relationship to work, the maximum possible useful work from either physical or chemical reactions to do work from us is at constant temperature is equal to the change in free energy. So that's the maximum amount. It's never going to be more than that. Typically it's less than that. Harry Bent is a thermodynamicist, and he came up with this idea: if you can't win, you can only break even, and you can't even break even. You will always lose energy. So what's the result? free energy in our system